And hello everybody, welcome back. So in the last video, we are talking about Wien's displacement law, one of the most important laws in radiation, and we saw how we can derive that from Planck's law. So we've basically covered some of the basics, and we know that for, let's say, a surface that's emitting radiation, okay, it's emitting radiation, we know that it is a function of, the heat output per unit area. So the heat output per unit area, where this is the area, it's a function of, okay, temperature. It's also a function of, you can discretize it according to the wavelength, for example. And yeah, also we need to take into account the direction in a 3D kind of sense. So this is a temperature variation. This is, let's say, lambda. Okay, wavelength. Okay, let me write that properly. Lambda. Alright. And this is direction. Sometimes books will like to use S. Okay, so how can we characterize direction? Okay, so this is what we're going to look into this video, so that we can see, okay, how you normally do directional dependence. So you can take a look at this. This is how we did it previously. Spectral emissive power, that's the energy per unit time per unit surface area per unit frequency. So energy per unit time per surface area, that's like the heat flux of some sort. We can characterize it by the frequency, but we can also characterize it, we know there's a temperature dependence and there is a sort of a directional dependence. Now, of course, for the black body case we were talking about last time, black body case, it's only a temperature dependence, and of course there will be some wavelength dependence. A black body will emit equally in all directions, so there's no directional dependence in that sense. So let's take a look at solid angle and what is it about. Okay, so we can start from this diagram, or little diagram over here. We can start from this little diagram. Oops, should close this. I'm gonna paste it here. Okay, so what's in this diagram? So let's analyze it slowly. We see that there's some unit area dA that's emitting radiation in all directions, and we take into account this direction S hat. Okay, so direction is S hat. You see this little S hat over here, and there's also this normal area. The area projected in the direction S hat is dAj. Alright, so this is the normal area, right? Okay, so remember there are two different areas we are talking about here. One is the dA, that is the area of this surface emitting radiation. The other dA double prime, this J, this is the surface area that's receiving the radiation. So just got to make that distinction there. This is the area receiving the radiation, and this is dA, is the area emitting the radiation. So we got to take that into account, and this one is the normal area. And if there was actually some actual like area dAj, you can see this dAj here, and it's angled at some angle theta j, so it's not angled normally, to this direction vector s. So we can say that dAj double prime equals to dAj cosine of theta j. So that's what this diagram is saying. Okay. So where does solid angle come in? So remember again, I'm just going to do a very quick recap. Remember how in angles, in a 2D angle sense perhaps, we have this length s, which is equals to r times theta, right? So for a small angle, this is r, this is theta, this length will be r theta. This is in a 2D sense. Alright, 2D. How about 3D? In a 3D sense, if you want to talk about using an area and relating that to an angle, you will need a solid angle. So the analogous way to define a solid angle is this. So, okay, so solid angle equals to dAj divided by r squared. So if let's say r is the distance from the center to wherever you are putting your area, just like this. So you have this solid angle is the relation between this normal area dAj double prime over r squared. Or if you want to put the actual area and this cosine theta, you can also do it like this. Alright, it's basically the same meaning. So the solid angle is like the 3D version of this picture that you see here. Alright, should already know this, so I'll run through it very quickly. Okay, so how do we have that? So if you take a look, okay, this is what they are writing here. Okay, so I think in this text they may have used the dAj double prime to represent the solid angle, because they put d omega equals to dAj prime, but maybe their meaning is different. But I prefer to use d omega to represent that solid angle. So just this is how I will define it. If the dAj double prime is this area projected, okay, I just use a different nomenclature. If it's like this, then how do we define the solid angle? Well, we can take a look at the little angles that are here. This is the psi. Okay, so what's on top? You have to put a r d psi, right? R d psi, this is the bottom length. Alright, let's see from here to here. This is the length r, and this is the angle d psi. So it's very similar to what we see here, r and theta. So this is r d psi. So that's the bottom. I'll just need to multiply. Alright, so what is this little angle over here? What's this length? Yeah, what is the length from here to here? Okay. Okay, I think I forgot something. Actually, this is not RD. Yeah, this is this length from here to here. Okay. Let me write this down here. Okay, this is much better. Alright, let's do the bottom one. This is not r d psi, this is r sine theta d psi. okay, because the length being measured is from here to here rather than this length. So this is r sine theta. The top orange line is r sine theta, so r sine theta decide is this red colored length. So I need to put that in. Okay, what about this length here? This is just r d theta. So d theta is this little angle here. Okay, I'll circle it out for you. This little angle here, and you have an r length in this yellow line I just drew. So this is r, or in this diagram they like to use s, but for consistency's sake I will just use r. So r d theta. Okay, so all in all, if you cancel the r's out, sine theta d theta d psi is what you will get. D omega equals to sine theta d theta d psi. So this is how we describe the solid angle. And if we want to have some spectral emissive power, alright, if we do it by we can divide it by frequency, by area, okay, by frequency, by area, and by the angles. We can do it like so. So the energy, the flux anyway, can depend on temperature, can depend on the frequency or the wavelength. So I'll just use nu, or rather theta, psi, and nu. So this is the spectral emissivity, and we also take into account the directionality of it by incorporating the solid angle. So sometimes we might write something like this. It basically means the same thing, because this omega means the solid angle, right? So this is where we start defining things like radiation intensity. Alright, so spectral intensity, I lambda, is the radiative energy flow per unit time, per unit area, normal to waves, per unit solid angle, per unit wavelength. So if you want to split it up by all of these, this is what we will use. Okay, instead of E we use I, because instead of taking into account the whole hemisphere here, we split it up by solid angles. So instead we use I here. So that's just the introduction to intensity. Okay, so this is how it's normally being defined. Alright, so spectral, this is how we quantify that radiation. So first, spectral intensity, this is what we are doing. We split it up according to the factors that are involved. Okay, so this will depend on some direction. Okay, according to this, yeah, some direction, some wavelength dependence, and some solid angle dependence related by S hat. But again, you must take note that when we are talking about this versus, let's say, this spectral emissivity, we are talking about two different things again, because they have two different areas, right? Okay, one is radiative energy flow per unit time, per unit area normal to the rays, per unit solid angle, per unit wavelength. Alright, anyway, yeah, I may have made a mistake. Okay, but let's do the diagrammatic, do a diagram so it's all clear. So let's take this picture here, put it like this. Okay, so we have this cute little picture, and what is this intensity talking about? So it's radiative energy heat flow per unit time per unit area normal to the rays. So what is this area normal to the rays? Okay, so the area normal to the rays in this case will be this area. Okay, it is this area here. So it's dA, the cosine of theta. So it's not this one, it is this one. All right. Okay, it is this one over here, not the one that's being over here. So okay, this area, this projected area here, will usually be quantified by the solid angle. Okay, this will be quantified by the solid angle. So this and this will be quantified by area. Okay, so these two are describing two different kinds of areas, but we don't want to do like oh, we have a per unit area here and a per unit area here. That'll be really confusing. You rather have a per unit area and then we have this solid angle thingy that's being used here. Okay, so yeah, this is basically what the how we like to measure intensity. So when we talk about intensity, there are two kinds. The spectral intensity, which is what we mentioned just now. This is done per unit wavelength, per unit solid angle and area. If you want to integrate across all the wavelengths, you just perform integration across all wavelengths as you see in this equation 1.30, and that will be just the total intensity. So yeah, just note the difference between spectral intensity and total intensity. So there are many different kinds of intensities. You just got to note what we are talking about. When we talk about spectral, we split it up by wavelength. When we talk about total intensity, we talk about the integral across all wavelengths. So we are not looking into wavelength dependence. So just to recap, the emissive power is integrating, let's say, the intensity over all solid angles, right? Because now this thing you split across all solid angles. So right, so for example, E equals to integral from 0, or rather over the whole solid angles, d omega, and you have this intensity here, I R S. Okay. Alright, so if you have a total emissive power, if you want a total emissive power, you do that. If there's a spectral component to it, just integrate over all solid angles. IRS and new. Okay, that's all. And so yeah, this is actually this equation here. This is actually this equation here. This is how we relate this spectral emissive power to intensity. So basically it's just integrating across all solid angles, and that's how we describe it. So now that we are talking about solid angles and intensity, we can start defining what is absorptivity and emissivity. Alright, because now we can describe the intensity of a body of any kind, and we can relate that to the black body. So if we relate that to the black body as a reference point, we can talk about emissivity and absorptivity. So thanks for watching this learning journal or radiation learning journal with me. So I'll see you in the next video.